All right, ladies and gentlemen, just wanted to wrap up some odds and ends and clarify some things that you should have seen throughout last week and also through this week. Just a reminder to expect a short quiz at the end of this week. Okay, so we've been talking about different types of energy, and this is something that a lot of you come from middle school with. But right underneath the web quest I published yesterday, I have a new set of slides. It should take you into something like this. Pretty basic. Okay, I wanted to boil it down to the basics for you guys just to give you what you need without confusing you too much. Okay, so the law of conservation of energy, we first need to take a look at different types of energy. Okay, and ultimately there's just two types. We have kinetic energy and we have potential energy. Kinetic energy being associated with some sort of movement or motion, and potential energy is going to be that stored energy. So, kinetic energy, I might have heat or electrical energy or mechanical energy. We have these different types, sound and radiation. Potential energy, we have, you probably heard of gravitational potential energy. A lot of you mentioned on the discussion post. Chemical, nuclear, elastic energy, and we'll talk about examples of all of those in a second. So, as far as different types of kinetic energy, we have mechanical energy, and this is the movement of any macroscopic object. And when we say macroscopic, I mean something that's big. You or I are macroscopic. A car, even a toy car or a rock, it's going to have some sort of mechanical potential energy. We have an equation that gives us that relationship. I left that in there. We're not going to need it while we're away from school here. Okay, another type of kinetic energy is thermal energy. We call it heat. We measure it, and the measure of amount of heat in an object is called temperature. Okay, so make that bold here. And believe it or not, the kinetic energy of the different particles of a substance gives it its heat. So, we should know by now that the particles and everything are moving, even if they're moving just a little bit. And the more they move, the more heat they have, so the higher that temperature goes. We can also have electrical kinetic energy, where I have a flow of electrons. Sound, right? Inside even your AirPods, there are little speakers, and if you look closely, you feel them. They are vibrating, and they're compressing substances, whether it's air or in the case of a headphone, there's some sort of polyurethane in there. It's making those air particles move, and they come and reach your eardrums. Moving on to potential energy, we have gravitational potential energy. Again, one that a lot of people remember from middle school. Okay, we also have elastic potential energy. And that is something that's stored because of an exerted force. So I can put elastic potential energy into a spring. If I compress it or I stretch it out, I have to put a force on that object to give it energy. Okay, whereas gravitational potential energy is just because of its position or its height, right? So if you've ever been on a roller coaster or a free fall at an amusement park, when you're high up, you have a lot of gravitational potential energy, right? We can also have nuclear and chemical potential energy. These are going to be more important in our conversation as we move forward. We have energy that's stored in the nucleus of an atom. We know that the nucleus is containing protons and neutrons, and around the outside there's electrons, and we have different assortments of them. They can be, move around in different numbers, which creates different charges, and in turn that gives us an amount of energy. At the same time, we can have chemical energy stored in bonds between different atoms. And again, that's something that we are moving towards, and that's why we're having this conversation. So the last thing is the law of conservation of energy. And that is saying that energy cannot be created or destroyed. It can only change forms. Okay, so that means in a system, and I try to define these things to the right here. In a system, energy can either be transferred or transformed. Okay, so when I look at a system is really just a defined set of stuff. So I could look at a whole roller coaster as a system. But that system would include the track and the chain that it takes to get you to the top, and the car that's riding on it, along with the people that are riding on it. So systems can be very fluid in how they are changing, but we need to define it at a certain point in time. So we might define it for one group of customers that it's going to ride that ride. So we would define it from when those people get on to when they get off. Okay. And these systems can transfer and transform energy. Okay. If I am transferring energy, I am giving the same type of energy to a different object. Okay. I like to remind people to think about transferring money. It's still money. It's just in a different place. I might transfer a couple dollars to my friend's account because he bought me lunch or something like that. It's still money. It's just now in his account. It's in a different place. Whereas if I transform energy, now it's changing forms. So on the, going from the roller coaster example, at the top of a hill, it's going to have GPE. As it goes faster down that hill, it is going to turn into kinetic energy. And I can see that in the simulation we did last week. Okay, I could go here, add my skater boy up there, and I can see if I add my pie chart, my energy is transforming back and forth from kinetic to potential. Now, if I were to pick a trend, I would say at the top here, he's got a lot of potential energy because he's really high up. Whereas at the bottom here, he's got a lot of kinetic energy. Okay, this is in a perfect world, right? We don't have any friction going on here. If I start talking about the real world, I start adding, I want to pause this so he doesn't lose too much. Add my pie chart. All right, as I go on here, I can see he's not going as high as he was in the other one. Okay, that's because friction is here. Right? In both of these settings, notice the size of the pie chart sort of represents the total amount of energy. Okay, so it's not getting any bigger. At the top of my ramp, I still have a lot of potential energy. I've got very little kinetic energy because he's not moving much up here, but I have this almost a quarter already of thermal energy. I've gone one more sort of lap around the track, if you will. I have that much more heat energy. So I am transforming energy back and forth between kinetic and potential, but also because friction is present, I have some heat being formed as well. So things don't go on forever because we have friction in the real world. Heat sort of escapes, and it's just something else to think about. So hopefully this helps, clears some things up. I would put these slides in your notes. Okay, I know I'm not able to get you your graphic organizers and stuff like that, but again, if I go back to these slides here, some really key points. I have two different types of energy. I've got all sorts of different types of that, different variations. But most importantly, the conservation of energy is stating I can't create it or destroy it. It just has to change forms or go somewhere else. Okay, so keep that in mind. Hope this helps. Shoot me any questions you have on Schoology, and we'll talk soon.